So we will begin the second part of our video on Chapter 9 review with question number 10. Now, we looked at this with the formulas approach and the dimensional analysis approach, and I guess I'll just keep that going with both ways. I again prefer the dimensional analysis approach. But when we see we have a 45, 45, 90 triangle, we will begin with the rules, and that is the legs are equal, and the length of the hypotenuse is equal to the length of a leg times the square root of 2. Also, we could use the reduced scale model for the basic 45, 45, 90 triangle, which again we want you to have memorized. And so in a 45, 45, 90 triangle, the legs are equal, so the legs in a ratio of 1 to 1, hypotenuse equal leg times the square root of 2, and so the hypotenuse number is square root 2. It gives us here that QS is 9, it's the hypotenuse, so if we were using our formulas, we would plug into there, so we'd have hypotenuse 9 equal leg times square root 2. To solve for a leg, we would divide square root 2, divide square root 2, and so we would have leg is 9 divide square root 2. Now we've learned that you can't have a radical in the denominator, and so we would rationalize the the prime involved in the denominator 2 is 2. We would want a pair of those. That means we need another 2 to go with that one. Once we've created a pair of 2's, then it pops out a 2 in the denominator. What you did to the denominator, you must do to the numerator to create equivalent fractions. And so then on the new numerator would be 9 times square root 2, which we just crammed together, 9 squared root of 2. We go through the 4 questions. Will anything reduce? Well, the 9 and 2 won't. You can't reduce the radical 2 with the other 2 because you can't reduce a radical with the number. Question 2, will a radical square root 2 break down? No. Question 3, is there a fraction inside the square root? No. Question 4, is there a radical in the denominator? No, so that must be it. 9 square root 2 over 2. It wanted QR and RS, which are the legs, and the legs are equal, so both QR and QS are 9 square roots of 2 over 2. That's the formula approach. Using dimensional analysis approach, we would say, well, what did we start with? And we started with the 9, which is the hypotenuse. So we're going to put the name of what it is with it. And so with scale models and dimensional analysis, we're going to take our start times our scale. And our scale is this picture here. So we're wanting to lose the name hypotenuse, so we put it on bottom, and gain the name legs, we put leg on the top. And we go to our picture and we say, okay, what was the leg number? And the leg number is 1. And what was the hypotenuse number? And the hypotenuse number was square root 2. So we've eliminated the name hypotenuse and gained the name leg. And so we get the leg is equal to 9 on top, square root of 2 on bottom, which is the same thing we had at this point. We rationalize the same way and get 9 square root 2 over 2. Again, I lean toward the dimensional analysis approach, but I'm presenting it both ways. Okay? Number 11 is a 30, 60, 90 triangle. As far as the formulas go, we have the length of the hypotenuse is equal to the length of the short leg times 2. And the length of the long leg is equal to the length of the short leg times the square root of 3. And then as far as the scaled down model goes, Give me just a second to make this do correctly. As far as the scaled down model goes, then we have this little triangle in a 30-60-90 triangle. The side opposite the 30 is the short leg, which is 1. According to the formula here, the hypotenuse is twice the short leg, so it would be 2. And according to this formula, long leg is short leg times the square root of 3, so it'd be square root 3. So there's the basic scale triangle for 30-60-90. It gives us, in this particular equation, the long leg 11. So we would have to plug into here to begin with if we're using our formulas. So we would have long leg 11 equals short leg times square root 3. We would undo multiplication by division, so we would divide square root 3. And we would have that the short leg is equal to 11 divided square root 3. Again, we would rationalize the denominator, and so we're going to multiply by square root 3 and get 11 square root 3 over 3 for the short leg, which is the ON. Now that we have short leg, we could plug that into the hypotenuse short leg formula, and so we would get hypotenuse equals short leg 11 square root 3 over 3 times a 2, understood to be over 1, and we would get that the hypotenuse is 22 square root 3 over 3. And the hypotenuse was OM. So there's the formula approach. We also want to look at the dimensional analysis approach. In the dimensional analysis approach, we're going to take start time scale. And with the triangle, we can do things that the formula won't allow us to do. Our start was 11 over 1, and the name of that 11 was long leg. We can go from long leg to either one using the triangle. Let's just go to short leg first. And so if we were going to do that, we would want to lose the name long leg and gain the name short leg. We go to the triangle and grab the numbers. The long leg number is square root 3. The short leg number is 1. And so we would get that the short leg is equal to 11 over the square root of 3. We then would rationalize and get 11 square root 3 over 3. We can also find the hypotenuse using the long leg from our triangle when there's no formula that says hypotenuse long leg. Let's look. We are given long leg. We're going to multiply such that we lose the name long leg and gain the name hypotenuse. In the diagram, long leg is square root 3 again, but hypotenuse is 2. And so we get that hypotenuse is equal to 2 times 11, which is 22, over 1 times square root 3, which is square root 3. We would then rationalize the denominator and get 22 square root 3 over 3, which is the same thing we got using our formulas. Any questions on 30, 60, 90, 45, 45, 90 triangle rules? We should memorize the things in red, the formulas, and the basic scale model. Okay? Number 12. Number 12, we have no angle measures given, and we can make no assumption about those angles, so don't just assume that this is a 30, 60, 90 triangle. What we're given is that GH is 5 and HI is 12, and we're looking for GI. What we know this time is two sides of a right triangle, and we're looking for the length of the third side, and we know to do that we'll use the Pythagorean theorem. The Pythagorean theorem says the area of the square at side A, given by A squared, plus the area of the square at side B, given by B squared, is equal to the area of the square at side C, given by C squared. It really doesn't matter which one you make your A and your B, but it does matter which one you make your C. Your C is always the hypotenuse, the one across from the right angle. So we're going to say the area of the square at side A given by 5 square, because side square is the formula for area of a square, plus the area of the square at side B, which would be given by the length of the side square, is equal to the area of the square at side C, which would be given by that square. So we have an equation. To solve the equation, we're going to use order of operations. We're going to do exponents before we add. And we're going to get 25 plus 144 is equal to C squared. We now can add, and so we get 144 is equal to C squared. So we did all that we could do to simplify. Now it's time to undo. We're going to undo the square with the square root. It teaches this to us on page 26, example 5. And we learned then that when you take the square root, you have to do plus or minus. And so we're going to get C is equal to 12, or C is equal to negative 12. But we know that when we're talking about distance, we can't have a negative, so we have to accept the positive square root value, because we're looking for how long is it between point I and point G there. Okay, any questions on number 12? Number 13, we're wanting to write an equation, and so we have to be mindful of the regression rules again at the first of the book. I believe they're on page P8. If not, flip a page or two before or after, and you'll find them. We begin by looking at the change in y, change in x, to try to determine whether this is linear, quadratic, exponential, rational, radical data. And so we will go to our table. The first change in y is a gain of 1. Its change in x is a gain of 9, so we have a 1 over 9. The next change in y is a gain of 1, and its change in x is a gain of 11. And so we get a 1 over 11. Don't forget to put the change in y on top. The next change in y is a gain of 1. Its change in x is a gain of 13, so we have a 1 over 13. We see that the change in y, change in x is not constant. That lets us know that this is not linear, and so we look to see what's changing. The change in x's or change in y's, and it's obvious to us that it's the change in x's that are changing. So we look for a pattern of change in the change in x, and we find that the pattern of change is a plus, plus, plus pattern. It's a plus 2. That tells us that it's a square root x, which is the same as x to the 1/2 power, and therefore we say that we're going to do a power regression on the calculator. Now we've investigated that the calculator will not always do really nice power regressions, especially if we have it in the form y equals something times square root x. And it'll do that, but it won't do it if it's got a plus something at the end. And so what we're going to do is we're going to do the paper pencil method that is being taught in this text of how to come up with this number and this number to go with our square root x that we already know. Okay? So I'm going to kind of clear the board on that other side so that we can do our little trick. So what we want to do is we have our old x's. Our old x's were 16, 25, 36, and 49. And what we want to do is get some new x's by taking what we know so far, square root x. And so what we're really doing is we're going to think of square root x as an x. And if we do, then this would be the slope and the y-intercept of what becomes linear as we change that. So we're going to get us some new x's, which will be the square root of the original one. So square root 16 is 4, square root 25 is 5, square root 36 is 6, square root 49 is 7. So we're eliminating those old x's, and we're putting those with the old y's. I missed the 7 there. 7, 8, 9, 10. And we know that since we're dealing with linear, we only really need 2 points. And what we're trying to do is find the slope and the y-intercept. To find the slope, we do change in y, gain of 1, change in x, gain of 1. So my slope is 1 over 1, which is 1. That means that in that position, I have a 1. To find the y-intercept, I pick a point. The first one is 4, 7. And the slope, which we came up with, of 1. And I'm going to plug it into y equal mx plus b and solve for b, which is the y-intercept. So I put my y in place of y7, slope in place of slope 1, x in place of x4, plus b, and solve for b. So I'm going to have 7 equal 4 plus b. Subtract 4. I get b equal 3. And so there's going to be a 3 in the b position. So my equation should be y equal square root x plus 3, because that 1 is understood. We can test it. Plug in a 16. Square root 16 is 4 plus 3 is 7. That's correct. Test it again. Square root 25 is 5 plus 3 is 8. Worked again. Test it again. Square root 36 plus 3. Square root 36 is 6 plus 3 is 9. So we tested out our points in our equation that we got, and we found that we found the correct equation. Any questions on number 13? Okay. Number 14, we're not sure what it is to begin with. You do realize that we could just plot those points. This is a point. Whoops. We could plot the points and look with our eyeballs and see what it looks like. Does it look like a linear? Does it look like a quadratic? Does it look like an exponential? Does it look like a square root? And then we could go to the calculator and do the proper regression. Or we can look at the change in y, change in x, and determine what it is. And we want to do it with the change in y, change in x. So the first change in y here is a gain of 2, and the change in x is a gain of 1, and so I have a 2 over 1. The next change in y is a gain of 2. Its change in x is a gain of 1, so I have a 2 over 1. The next change in y is a gain of 2, and the change in x is a gain of 1, so I have a 2 over 1. The change in y, change in x is constant, so that tells me that this is linear. And if it's linear, then this constant rate of change is the slope. And what we need to go with slope, if it's linear, is the y-intercept. And to do that, we pick a point. We'll just choose the first one, 5, 13. And the slope, which we've already come up with, of 2. And we'll plug those into y equal mx plus b, and we'll solve for b. So we'll put the y in place of y13, slope in place of slope 2, x in place of x5, and then we'll solve for b. So we're going to have 13 is equal to 10 plus b. We're going to subtract 10, and we're going to have b is equal to 3. We have the slope and the y-intercept. So our equation is y equals slope 2 times x plus y-intercept 3. Again, we could test points, plug in a 5, 2 5s are 10, plus 3 is 13, so it worked out, and you could check the rest and they would work out also. Any questions on Chapter 9 review?